I have horrible news, and that's that my pink marker just ran out of ink, and I'm really upset about it. So now I'm just going to be back to using the boring old green. Statistically, at least one of you is colorblind, so maybe you won't notice the difference between these two, because this is like nearly red. But, oh geez, okay. I will persevere nonetheless, and we'll get to talking about compound interest, which is this other slightly more complicated form of interest. Again, it involves a lender and a borrower, and the amount owed increases over time. And many of you were hinting at this type of behavior when you were doing the activity in class on Tuesday, where you asked, every time you apply the interest, are you applying it to just the principal, or are you applying it to everything that's owed? Now, for simple interest, the interest is only applied to the principal after each cycle. But for compound interest, it's actually kind of like what some of you were saying, where interest is applied to the amount owed at that time. So it's like in the example of that problem where you borrowed $500 and the rate was 10%. So then after 1 week you owed $550, but then after the second week you owed $600 because you added, so this was in the simple interest case, you added 10% of the original 500 every time. Compound interest would be if you applied the 10% to the total amount owed at that time period. So if you applied the 10% to the 550, so this would be adding, instead of adding 50 to 550, you would add 55. You'd divide this by, you'd multiply this by 0.1, and that would give you 55, or 550 plus 55, which is 605, I think. Yep, that should be right. Math is hard sometimes. Now, this makes it sound like an iterative process, but it can actually be generalized to just a function of time, so I'll talk about that in a second. But first, as usual, I'm going to put down an example. And this example is a certificate of deposit, a CD, which is kind of like this mix of an ordinary savings account and a bond, where you can lend money to a bank or a credit union, and then interest will be paid on it to you in the form of compound interest. So let's say that we have a CD. Let's say that you buy, or you invest in a CD, $1,500, compounded annually, with R equals 4.8%, which of course is equal to 0.048. I'm kind of running under the assumption that you're comfortable with converting decimals to, that you're comfortable converting percentages to decimals. But if this part confuses you, you can always ask me about it, and I'm sure that you'll get it very shortly after that. So, like you might have expected, this compound interest story still has the fundamental elements that we had before with simple interest. So fundamental elements. And those are P, the principal, T, time, R, rate, I, interest, and F, final payout. Now, for this, we kind of ignore interest and we pay more attention to the final payout, so I won't ask you too much about the actual interest, but to get the interest, you would always just subtract the principal from the final payout if you wanted to. And the formula that you get to relate the amount of time to the final payout and the principal is F equals, and then P times 1 plus R to the T. So this is now raised to a power. And this is where you get when you convert the iterative process of applying interest to the amount owed at each time step to just a function of plain old time, where you don't have to go through every cycle to figure out what's going on. So in the case where like something doubles every time, you would just have, whoops. So if the amount, say the amount of money were to double every time, that would be equivalent to an R of 1, because you're getting 100% interest every time. So that would be equal to P times 2 to the T. And so this would be, and if you think about it, so if you start with $100, then at the next step, at step 2, you end up with $200, and then at step 3, you end up with $400. You get that by just plugging in 1, 2, or 3 into this T here. So that's particularly useful. Okay, so in this case here, we have that we invested this much money, so this is our P, and we have our R is given to us here. And so we can compute the final payout at various points of T. So if we set up a little table here, let's just take a look at how this ends up. F, which is equal to 1,500 times 1 plus 0.048, or 1.048 to the T. Let's check it out at 1, 2, 5, 10, and 15. And so just plugging these values in for T, we get 1572, 1647. At 5 we get 1896. 0.2 or 0.26, and actually this is a 0.46 on it that I miss. I should be adding the cents to each of these. And then we get 2,397 and 20 cents, and at 15 we get $3,030.47. So these are all in dollars. Okay, so that's great and all. We can see that this is growing. Maybe what you can't see from this is the rate that it's growing. But generally, this is what's called exponential growth. So we'll have some super linear function where it's just kind of curving upward like this. Whereas in the simple interest case, so this would be compound interest, and then in the simple interest case, we would have just had linear growth as opposed to exponential. So this is much faster. Good for you if you're the lender, not as good for you if you're the borrower. Okay, so now I'm just going to change up this problem a little bit so I can show you some quick examples of how to solve for various parts of this compound interest story, because it becomes a little bit harder than with simple interest. So erasing this table. Let's say we're still investing 1,500, but let's say after 2 years, the CD is worth $2,000. Now, what is R? What is our rate? So let's just set up the formula here. So we've got final payout, principal, and our time. And so we can put those all into the equation. So let's go ahead and do that. So 2,000 equals 1,500 times 1 plus R, we don't know R, squared to the 2, plugging that in for T. Okay, so now let's go ahead and divide both sides by 1,500 first, because that seems like the first thing that we should do. So doing that, 1,500, 1,500. Okay, so these two will drop out, and then 2 over 1.5 is the same as 4 over 3, so this becomes 4 thirds right here. And then we've got 1 plus R squared. And now, to solve for R, really we need to solve for 1 plus R. And so to do that, we can take the square root of both sides. And so square root of 4 thirds is equal to 1, whoops, let's see, 1 plus R, right? Because the square root of something squared is just the thing. Okay, so now just moving this 1 over to the other side, we have that R equals square root of 4 thirds minus 1. And okay, wonderful. So I can pull out my calculator and check out exactly what that is. So we've got 4 divided by 3 is that, and then square root of that is 1.15, and then subtract 1 from that, and we get that our rate must have been 0.1547, or 15.47%. Cool. So that's how we would solve for R. That's actually a slightly easier problem than what's coming next. So next, let's say that we had to actually solve for T. So let's say let's say so now we're still, let's change up the question again. We still have a principal of 1,500, but instead, next, we will set R equal to something. So let's say R equals 0.1, so 10%. How long before the CD is worth $2,000. So now what we have is our F and, or sorry, our P and our F and our R, and what we want to know is T. So let's go ahead and set that up. So let's do, again, 2,000 equals 1500 times 1 plus 0.1 or 1.1. I hope everybody's okay with that. This is 1 plus 0.1. And then raised to the t. Okay, so, and I'm just going to throw an extra set of parentheses around here, or brackets, just to indicate that the t is in fact only operating on this 1.1, not the 1500, just to make it extra clear. So now, again, we're going to have to go ahead and divide out this 1500, so let's do that. These turkeys drop out of the sky, and then we have that 4/3 is equal to 1.1 to the t. Okay, great. Now what? How do we get a variable? How do we get the identity of a variable which is in the exponent? Now, a lot of you are like jumping up and down in your seat. I know how to do it, but most of you are like, oh, what? I don't have any idea how to do that. And I will tell you that this might ring a bell, but now logarithms are going to rear their ugly head here. And more specifically, what I mean is that we're going to have to wrap both sides of this equation in a logarithm with the base 1.1. So, doing that, and I'm just going to move my work up into this zone here, where it's more likely to be in the camera shot. Just going to rewrite the formula a little bit more compactly over here. Okay, so wrapping both sides, well, first I'm just going to, so wrapping both sides in a logarithm with base 1.1, we'll have log base 1.1 of 4/3 equals log 1.1 of 1.1 to the t. And now I'm just going to put a little section of useful log rules over here, and I'm going to write them down as they become useful. The first useful log rule is that a log of any base of any number, a, raised to a t, is equal to that t multiplying the whole log. So t times log of b to the a, where the a is no longer raised to that t. So here we'll just do the same thing. So log 1.1 of 4/3 equals t log 1.1 of 1.1. And now the next useful log rule is that log base b of b, if the argument is the same as the base, it's just equal to 1. So, whoa, there is a bug in my room, a flying, buzzing insect. It tried to kill me just then. But don't worry, I'm alive. Okay, so now applying that, this whole turkey here just becomes 1, and we end up with just t on this side. So log base 1.1 of 4/3 is equal to t. So now we have solved for t, but we still don't really know what this dingus is here, so we need to figure out about that. And how do we do that? Because I don't know how to put log base 1.1 into my calculator, right? That's like some weird button that probably I have to press second, shift, whatever to do. This is where one last useful log rule comes in, and that is if you have log base b of a, that's equal to, and I'm just going to drop this down to the next line here, that's equal to the natural log of a. Natural log is the log with e as the base. Not super important, but natural log, ln, is a button on your calculator, or it should be, divided by the natural log of b. So that's what I'm going to use next. So I'm going to say t is equal to the natural log of 4/3 divided by the natural log of 1.1. And that I can plug into my calculator a little bit more easily. So let's go ahead and give that a try. So the natural, whoops, I know how to use my calculator. 4 divided by 3 equals this, natural log. So it's 0.288 roughly, and then divided by 1.1 natural log divided by 0.095. And now dividing this fraction, we go 0.288 divided by 0.095, and we have that this is roughly 3 years. So I figure this was pretty math intensive with the roots and the logarithms, and so if any of this is confusing to you, we'll have plenty of more chances to practice it, but I just wanted to show you off the bat how to solve for the various parts of this problem, because it is a little tricky. You have to remember some of the things that maybe you haven't seen in a little while from your high school, elementary school math classes, whatever. So that's all I had for now, and we'll jump back into practicing with these things on Thursday, and it should be great. So I'll see you then.